I'll have my office hours this afternoon and be available for discussion at 2 o'clock. All right, so let's see. We were reviewing something very fundamental last lecture, the density operator, start of our show. So one should think about the density operator as the most general description of the quantum state. And the quantum state is nothing but a vehicle for calculating the probabilities of measurement outcomes. And if we have the quantum state, we can always calculate any probability for any kind of measurement we could do. We can use the density operator to find those probabilities. So for example, if we have a so-called projective measurement, which is to say a measurement whose measurement outcomes correspond to eigenvectors typically of some Hermitian operators, or more generically we say we're doing a measurement in a basis, which is to say that the measurement outcomes are associated with projectors onto those directions in Hilbert space. These are one-dimensional projectors. We can talk about things more general than that. But in any event, given this sort of standard kind of measurement, then we can write the probability for finding that measurement outcome as the trace of rho with the projector corresponding to that direction in Hilbert space. And that is another expression, is just say we're looking at the diagonal matrix element of the density operator with respect to that element of the basis, this projector. We know how to take the trace, doing the famous rule. And so that gives us the Warn rule. Okay. And as we've emphasized many times now, importantly, the off-diagonal elements of the density operator are what we call the coherences. And they tell us something about the possibility of observing quantum interference between those outcomes. Okay. So, importantly, we break up our states into two classes, pure and mixed. Pure states are states where they're the generalization of what we think about as a vector in Hilbert space. They are themselves one-dimensional projectors onto that state. They have the property that the trace of rho squared is 1. And the idea of purity here is to say we have maximum possible information about the quantum system that we could have consistent with the uncertainty principle, or quantum mechanics, however you want to say it. In contrast, a mixed state we can always think about as some ensemble of pure states that are weighted with some classical probabilities. And then that state would be what we call a statistical mixture of those pure states, weighted by those probabilities. As I said, and you'll see in your homework coming up, this decomposition is not unique. Okay? That is to say, there are many different ways, uncountably infinite number of different ways I could write a density operator in terms of a statistical mixture of pure states and get the same density operator. And from the point of view of the observer, the statistics would be the same. Here's a trivial example. Suppose I have, we looked at this in a kind of contrived example, but what the heck, we'll just continue that picture where imagine a preparer flipping coin and sending you a particular pure state. Now, we looked at the example where the preparer flipped the coin and either sent spin up along Z or spin down along Z. Okay, right? And if it was a fair coin, 50-50, that state was that state, right? Statistical mixture of spin up and spin down. But suppose the preparer did something different. Suppose the preparer rotated her Stern-Gerlach apparatus and sent you either spin up along X or spin down along X with the same coin. What would the state be? Well, it would be, in that case, 50% of the time she sends you the pure state up along X, and 50% of the time she sends you the state spin down along X. But these are the same state. These are both equal to 1/2 times the identity operator. So from your point of view, you get random statistics, completely random. No matter what you measure, you're going to see something, but you get that completely randomly every time. Because this is the completely mixed state. And so if you were to do many, she would send you many, many, many times. Each time you do it, you get a random bit, and you would see complete randomness in that case. Of course, from the point of view of the preparer, she has a lot more information. She knows whether she sent you spin up along X or spin up along Z. So if she sent you spin up along X and you choose to measure spin up along X, she knows with certainty you're going to get spin up along X with probability 1. The outcome doesn't change. It's just the probability of what outcome you're going to get is different depending on who has what information. Okay? But from the point of view of the receiver, who doesn't have the information about whether the spin was sent up along X or up along Z, or from that, the point of view of Bob, DC is a completely mixed state. So these two states are the same. And there are generalizations of that, and we'll see them. All right? Very good. So just again to emphasize, you know, there are states we know about. We always talk about in classical physics, but in quantum mechanics, if we wanted to talk about, say, a thermal state, a state that represents a system in thermal equilibrium, that state is a mixed state, unless it's at 0 temperature. That state is a statistical mixture in the canonical ensemble of the energy eigenstates. I mean, there should be a degeneracy factor or something like that, you know, right? So that's an example of a mixed state, a thermal state. Now, again, there's missing information. The missing information is, you know, something about, as the system thermalized, information got lost somewhere. Otherwise, I'd know exactly what the energy eigenvector was. So this is an example of a mixed state. And that missing information doesn't have to come from some cognitive, you know, cognizant being who prepares us one state or the other. It could be stored in the correlation with other particles. If we knew what they were, we would be able to purify our knowledge and have a more pure assignment of the state. So there's an intimate relationship, as we will see, between pure versus mixed and entropy. So pure states have no entropy because we have full information, whereas mixed states have more entropy because there's missing information. So entropy is another word for missing information. Right. And the way in which we quantify the degree of mixedness, one way to do that, we could do it through the entropy. This is sometimes called the linear entropy. But this is the simple thing to do, is to calculate the trace of rho squared. And if I have a finite dimensional Hilbert space, the minimum value of that is 1 over the dimension of the space. And for the pure state, as we said, the trace of rho squared is 1. Right. So again, I just want to emphasize this over and over again, the difference between what we call a coherent superposition versus a statistical mixture. This state is a statistical mixture of spin up and down along Z. It's the completely mixed state. This state is a coherent superposition of spin up and spin down along Z. And the difference is seen in the off-diagonal matrix elements of the density. All right. Any questions? Okay, let's continue then. So, we're going to now talk, as we will, for the remainder of the semester before fall break, about quantum coherence in absorption and emission of light. Okay. So let's just quickly set the stage here. We're going to talk about atoms because they're simple, although the general ideas easily generalized to molecules and condensed matter, but we'll just, for the moment, stick with atoms because that's what I know, and it's easy, they're the easiest piece of matter to talk about. So we have some Hamiltonian for the atom, and that Hamiltonian we can write in terms of the energy Eigen vectors of the system, the bound states plus, the unbound states. So I'm just, when I write n here, it's really all the quantum numbers that would really denote the energy. So there's some ionization threshold. This is the Hamiltonian for the atom written in the basis of its energy. And then we want to talk about absorption and emission. Well, we have some interaction Hamiltonian, and we're looking at the interaction with electromagnetic fields. If we're thinking about this in terms of absorption and emission, we are typically thinking about a field with some spectrum of frequencies, and we're looking at the case, typically speaking, where the wavelength of the magnetic wave is big compared to the size of the atom. Yeah?
Here missing the first step, H. Is all degenerate?
Oh, I'm sorry. I'm missing the energy. Yes. Yes. Pardon me, of course. Thank you. Yes, indeed. Otherwise, that's just the resolution of the energy. Right. So, we're going to look at the case where the wavelength is much, much bigger than the Bohr radius. And in that case, we can make a multipole expansion in thinking about the interaction of the field with the atom. Okay. So then this is, we can make a multipole expansion. And think about, well, there's some overall charge of the atom, right? And we have the charge, this is if I have an ion. And then I would have generally something that would look like this. So, in this notation, R is the center of mass position of the atom. And for the moment, we take that to be a classical variable, although we might not want to. We might want to think about the motion of the atom as quantized itself. But under simple circumstances, we can treat that as a classical variable. And this is the electric dipole moment. Which I can think about for one electron, valence excited electron, then I can think about this as the charge of the electron times the position of the electron, bless you, relative to the nucleus. Okay, so that's what this R is, that's the position of the electron. And then I will have a magnetic dipole moment, which generally would have components that involve orbital angular momentum and spin angular momentum that would contribute to the magnetic dipole moment. Okay. Right. And if we think about a monochromatic field, I'll write the electric field at the position of the atom as the real part of some complex amplitude with some phase at the position of the atom with some frequency, which I'll say is the frequency of the light. Yeah?
One thing I always wondered about is this depends upon the origin of the coordinate system. Like you could put the origin over in the other state, and then the dipole moment would be bigger.
So if I have a neutral system, the dipole moment which is integrated over both the positive and negative, is relative, will always be independent of origin. So in this case, if I have a nucleus, this is a problem we always get, or I always get in E&M. If I have a neutral system with an equal amount of positive and negative, then the dipole moment itself is independent of origin. It's this vector. It's the relative vector between positive and negative charge. If it's not neutral, it gets more complicated, but then these two terms together make it all work out. The physics can't depend on the coordinate system, and that's how it works out.
Oh, I see. So in other words, later on we forget about that Q part.
Yeah.
But I forgot that we.
If it's a neutral part,
about it.
yeah.
No, because when we're doing, we just do the electron.
That's right. And we're treating this as, in this case, it's a neutral particle. So this part is 0, and this, in that case, is that independent origin. Otherwise, we have to think about both terms together.
So in other words, before you throw out that first term, you have to remember, oh, this is with respect to the center of the neutral system.
That's correct. Good. All right. All right. So, with this said, if our dominant term, unless for some reason this term is 0, so if we have a neutral term, we forget about this. The dominant term in the multiple potential will be the dipole, the electric dipole interaction. Unless for some reason, as we'll see, this is 0 for some other reason. And then we would go to the next term. We might have a magnetic dipole allowed, or electric quadrupole, or what have you. Okay? But the dominant term we typically think about is the electric dipole. So in that case, with this said, my interaction Hamiltonian looks like in the electric dipole approximation. Which is the dominant multipole here. And typically an excellent approximation for atoms. Because atoms are, about an angstrom big, and the wavelength is about a half a micron. All right. So, yes, sir.
How long is an angstrom again?
What's that?
How long is an angstrom?
10 to the minus 8 meters.
Okay.
I mean, no, sorry, 10 to the minus 10 meters. Yeah.
Okay.
Yeah, so I'm thinking about 10 to the minus 8 centimeters. Yeah. Mr. CTS here. All right, so this is typically called the positive frequency component for reasons that we'll come back to later, and this is the negative frequency component that modulates our plus and minus frequency component. Now, you may remember, if you studied this, if we look at time-dependent perturbation theory, and I want to know what is the probability so let's say that I have some, energy levels of my atom here. And let's say I start the system in the ground state. Yeah?
An alternating sign on the relative phase, the E phi, EDI phi. They're both positive. Should they be alternating?
Yeah, I meant to say minus. And of course, this, I mean to say minus as well. So, thanks.
They're both negative terms though?
This, what do you mean? The overall sign, this sign has to do with this, and it's kind of reversed because of the way we do things in physics. So the positive frequency component is the one that oscillates like either the minus I omega t, and the negative frequency component oscillates like the plus I omega t, because that's how we define it. Okay? All right. So let me remind myself what I wanted to say here. Yes. Okay. So from time-dependent perturbation theory, you may remember that I would say that the probability of making a transition from some initial state to some final state would be equal to the following thing. I'd have the matrix element of the positive frequency component of the Hamiltonian, the matrix element squared, divided by the energy denominator, the difference between the energy, where I've added h bar omega, times some sinc function, sine function here. And then I have the term with the negative frequency component. Where this is the Bohr frequency relative to this energy over h bar, and this is the other way around. Yes, sir.
This first started.
That's right. Well, this is, in first order perturbation theory, this is the probabilities. So this is from, if I were to just do standard time-dependent perturbation theory, this is what I would find. Now, of course, what we see here is the important idea of resonance. When the final energy, in this case, is equal to the initial energy plus this amount of energy, this term completely dominates over this, for only those final states for which this is true. And similarly, there is the other way around, where if I subtract this energy from whatever this final state is to this initial state, then this term would dominate. So this is the term that, with a positive frequency component, says something about absorption from this point of view, whereas this term says something about emission. Absorbing a photon or emitting a photon. Yeah?
The units on the left are dimensionless, right?
There is square missing units. The denominator.
Oh, the denominator, so you're missing a square in the denominator. Yes, thank you. And that's the amplitude, is the probability. Yeah. Thank you. All right, but the important point here is resonance. That when the frequency of the oscillating field is tuned near to the resonance, Bohr frequency resonance, then the probability to go into that state dominates over anything else that is not near resonance. And from that situation, we start our journey into the discussion of two-level atoms. So, in quantum optics, we love to talk about two-level atoms. You know, people sometimes say quantum optics is about two-level atoms and harmonic oscillators. It's about it. So our two-level atom is the situation where we say, well, there's two levels. We typically call them the ground state and the excited state. They don't have to be the absolute ground state of the system. We can take two levels, one lower than the other, and we typically call one the ground state, the other the excited state. But we'll think about this for the moment as this being the actual lowest energy level. And some excited energy level, whereby we tune the laser, say, light, to be close to resonance with one level. Okay? Now, whether I can ever do this exactly, there are really no two-level atoms, right? There are always other nearby levels, and we can ask how far off resonance they are, and do they contribute some amount to my dynamics? But for the moment, we'll focus on isolating through resonance just two discrete levels of my atom. Okay? And the difference between these is known as the detuning. The detuning is the applied frequency minus the resonance frequency. The resonance frequency is the Bohr frequency. Okay? So that's my two-level atom. And now I want to, with my two-level atom, in this case, the Hamiltonian of the atom is easy. It's this. That's the Hamiltonian for the atom. We have those two levels. And the interaction Hamiltonian is as we wrote it there in the dipole approximation. But now we're going to take that interaction Hamiltonian and we're going to project it onto this two-dimensional subspace. where my resolution of the identity is this. Okay. So I've just taken this and I said, I'm going to look at it only in the subspace of Hilbert space associated with these two energy levels. Okay. So now we have to think about the matrix elements of the dipole operator with respect to this basis. Right? So what we said here, the dipole operator, we said is the charge of the electron, think about it as one optically excited electron times the relative position of the electrons with the nucleus. Now, one thing to note about this, of course, is that this is an odd parity operator. And my eigenstates of the Hamiltonian for my atom are eigenstates of parity, right? Because of the fact that we have this spherical symmetry in the Coulomb interaction between the nucleus and the charge. So the eigenstates of the Hamiltonian are eigenstates of parity. Typically, have something like a YLM in them for, if I think about them in terms of having some definite orbital and momentum, and those are eigenstates of parity. So, given that fact, what can you tell me about the matrix elements of the dipole operator with respect to these states? For example, what is this matrix element? 0. It has to be 0, right? Because this is equal to, if I wrote this as an integral, and this is symmetric with respect to the probability density must be symmetric, and this is anti-symmetric with respect to flip, so this has to be 0. And similarly for the excited state. So that is to say, the eigenstates of the atom don't have a dipole moment. The off-diagonal matrix elements, on the other hand, can have and of course, that is one of the selection rules for dipole absorption. You have to have opposite parity states in order to get a dipole allowed transition. For example, if this is an S state of, say, the ground state, then what is a possible dipole allowed transition? What is a good P? I have to have a P state for two reasons. One, it has to have the opposite parity, and the parity is -1 to the L, and the other is that I can only change L by 1 or 0, and in this case I have to change it by 1. Okay, so in this case this might be in cesium 6s, and this would be 6p. I figured that. All right. Right. So, with that said, my dipole operator looks like this, where DEG is the matrix element of the operator. It only has off-diagonal elements with respect to that basis because of parity. And we would plug that into these expressions here for the interaction Hamiltonian. All right, So, with that piece of physics in hand, we now can just abstractify, as we will, for the remainder, and think about our two-level atom as a qubit. As you know, a quantum bit or a qubit we think about as any two-level or two-dimensional Hilbert space is the space of a qubit. And we'll be talking about them for the next few lectures. And typically we would say the standard basis, we have a state we would call 0 and a state we would call 1. Also, if we thought about this from the point of view of quantum computation, we'd call this the computational basis. So examples of this are the two-level atom. That's an example of a qubit. I can think about a qubit as, say, polarization states of a photon, where I might say I have two orthogonal polarizations and choose one of them, say the horizontal state to be logical 0 and the vertical polarization to be logical 1, for example. Could encode a qubit in a photon, the states of like as we'll see in our homework. Or the standard picture, as we will importantly connect to, is thinking about a spin 1/2 angular momentum. Whereby the standard basis we assign 0 to be spin up and 1 to be spin down along the quantization axis Z. So in manipulating and thinking about absorption and emission with two-level atoms, connecting this to the algebra of spin 1/2 is critical, and I want to quickly review that here. So, spin angular momentum. We have our angular momentum components satisfy the usual commutation relations. We define the raising and lowering operators in terms of those components. We satisfy these commutation relations. Let's see what I want to say here. sorry. Sorry, can't straighten my mind. Z. It's not the sun, it's just getting confused with me. That's right. And of course, we have the eigenstates of the Z component and the raising and lowering. So for spin 1/2, we have the nice result that S plus or minus, we have the two states, so we have the raising and lowering operators don't have any factors in this case. This being spin up along Z, and this being, what did I just do? Spin down along Z. Right? So this is our standard angular momentum algebra. And as you know, we defined the Pauli operators to make our lives simpler and get rid of all the 2's and the h bars. So we define the spin operator, we factor out the h bar over 2 for spin 1/2, and the Pauli operators remain. Right? So that sigma x, for example, is Sx divided by h bar over 2. Now, one thing that's always confusing is the way we define the Pauli raising and lowering operators, sigma plus and sigma minus. We don't put the factor of 2 in that, because otherwise we lose this nice fact that we don't have any factors of 2 in the raising and lowering operators. So we define these as just S plus or minus, but just get rid of the h bar, but not the 2. It confuses all the time to try to get the algebra right, but there's no 2 in that, but there's the 2 in the x and the y. That's just how it is. So, what do we know? We next know we can write the Pauli operators in the standard basis. This operator is diagonal with eigenvalues plus or minus 1, because the SZ has eigenvalues plus h bar over 2 and minus h bar over 2, right? Which in the standard basis is this. Sigma plus takes spin down, to spin up. That's what it does. Which, of course, is that matrix. Sigma minus is the Hermitian conjugate of sigma plus. It takes spin up to spin down. And it has the 1 on the other side. Sigma x, according to this, is the sum of sigma plus and sigma minus. Because Sx, S plus is xx plus I sy, and S minus is Sx minus sy. You add them together, you divide by 2, you get this. Therefore, this matrix looks like this. And sigma y is the imaginary part, sort of, or the anti-Hermitian part, but without the factor of 2, because of the way the 2's are defined. Yeah?
Sorry, I'm going to come back over here for a minute. Should that be sigma z?
Where? Which one?
When you talk about the first column matrix?
This?
Yeah.
I'm just saying, this is an example. The sigma x component
Okay.
is related to Sx component by this sort of way. Yeah?
In the commutator of SZ and S plus minus, on the right-hand side, is there some H-bar factor?
Oh, I guess there is, isn't there? H bars be damned, but yes, there should be H bars in both of these expressions. I want to be careful. We throw our H around our H bars fairly loosely. So most of the time we don't use them anyway. Okay, and sigma y thus is this matrix. Now, I command you, if you haven't already done this, memorize the Pauli matrices. You must have them in your head. The only one that Owen ever gets to do is this the minus sign or is that the minus sign? That's the only thing that is ever in question. You have to kind of remember it, or you have to rederive it in some way to know. The other ones are fairly obvious once you do it for a little bit. Oh yeah, this guy is diagonal, and this guy has one of those sigma x. It is the sum of that guy. But whether this is the minus sign, that's my another thing that and no one ever remembers. All right. So the Pauli matrices, indeed. Let's see. Other properties. The Pauli matrices satisfy. So if I take the factors of h bar and 2 away, then we have these commutation relations of the Pauli operators. That's this guy over here, taking away the h bars and 2s, you can introduce a new 2 over there. The anti-commutator. So with the brackets, this is the sum rather than the difference as the commutator. From these relations, it follows that if I doesn't equal j, it's 0. And if I does equal j, well then it's one of these guys squared, which is the identity, so this is twice the identity delta ij. Okay. So importantly, the Pauli operators square to the identity. taken together, we can see, if I look at the product of two pallies, then this is equal to I times epsilon ijk sigma k if I and j are not equal, and if I and j are equal, it's equal to the identity. So you can always look at the product of two pallies. If they're equal, well, it squares to the identity. If they're not equal, then they're I times the cyclic permutation of the other. So for example, sigma x times sigma y is I times sigma z. Now, one thing that follows from this is kind of weird. Of course, as the Pauli operators, sigma x, sigma y, sigma z, were related to the components of angular momentum, Sx, Sy, and Sc, they are Hermitian. Not sigma plus or sigma minus, but the components x, y, and z. Now, if I look at, say, then sigma dagger sigma, this is Hermitian, so this is the square of that guy, which is the identity. So strangely, these matrices are also unitary. The Pauli matrices are both Hermitian and unitary. That's kind of weird, but it's true. Right. The eigenvalues. What are the eigenvalues of this guy? Well, the eigenvalues of sigma z are +1 and -1, right? So what are the eigenvalues of sigma x? They're +1 and -1. Any one, because they are all related to one another by a similarity transformation. Okay? So the eigenvalues of any component are +1 and -1. And the trace of one of these guys is therefore what? 0. So they're traceless 2x2 Hermitian matrices, or the Pauli matrices. Very good. All right, let's see, what else? Oh yeah, okay. So very importantly, the Pauli matrices, together with the identity, the 2x2 identity matrix, which we typically write as sigma 0, sigma 1, sigma 2, and sigma 3. So this is x, y, z, in the standard kind of Einstein index notation. And this is the identity. So this is sigma x, and this guy is, this matrix is there, y and z. Okay? So those Pauli matrices form a basis for all 2x2 matrices. Now, just want to emphasize this important point if you haven't thought about it before. The set of matrices themselves are a vector space. Okay? So if I think about any d by d matrices, form a vector space. That just follows from the fact that I can take superpositions of matrices, and they're also matrices. So I can take a matrix M1, oh, I have the hat on it, and put some coefficient, some scalar in front of it, add it together with some other matrix, and that's a matrix, another D by D matrix. Okay. What's the dimension of that vector space? D squared. It has D squared linearly independent matrices. Now I can also put on top of that vector space an inner product structure that gives me a notion of distance between matrices. And the easiest way to do that is to borrow the Euclidean inner product that we know associated with just column vectors. Thinking about the matrix, kind of, we can vet the matrix. So I think about the matrix, if my matrix, let's just say, was a 2 by 2 matrix, then vecting that matrix just means stacking the columns on top of one another. Right, so this 4 numbers now becomes a 4 column vector. And if I wanted to just think about the inner product of these two matrices, I just borrow the inner product from the column vectors. Now it turns out that that's equivalent to the Hilbert-Schmidt inner product, which is Euclidean inner product. That is to say, I can write an inner product between two matrices in my pseudo-Brockett notation. The dot product between those matrices as the trace of M dagger. That is equivalent to taking the dot product, I challenge you to show that, of these two column vectors with the stars on dots. Okay. So this is how we take the inner product of two matrices. Now, it thus follows from this that my statement is true. That I can write any 2 by 2 matrix as a superposition of the Pauli matrices. Or abstractly, operator on a 2D Hilbert space. A, I claim I can write it as the following. Okay, so this is a fairly loaded notation. This thing has both a vector and a hat on it. This is a shorthand for A1 sigma 1 plus A2 sigma 2 plus A3 sigma 3. Okay, that's what I mean by that notation. Is that clear? These are matrices, these are numbers. Okay. And how would I find these coefficients? So I claim I can find the A sub alpha by looking at the trace of this operator. Let's just say I look at the inner product, I look at the dot product project that guy onto that direction. Let's check. Let's check. So, this is her mission, so I don't need the dagger. Right? Otherwise, gotta rip the dagger. So, first, an aside. What is the inner product between two pallies? So let's check what this is. This is the trace of that with that. Let's do it for the case where this first. Let's just go with the case where this is 1, 2, or 3. So that's my notation without telling you. The alpha is if alpha goes is 0, 1, 2, 3, and this is that. Okay. So what is this trace? Well, we said that sigma I times sigma j was I epsilon ijk sigma k plus plus the identity delta ij, right? Remember that little rule? So what is the trace of sigma? 0. And the trace of the identity is 2. So the two Pauli matrices are orthogonal to one another. And along the same direction, they have length 2. Okay. And so thus, this follows. Again, I command you, because I have the power of command, to memorize this. This is extremely useful. We use it all the time. All the time. If you're dealing with 2x2 matrices, you better use this. Okay. For example, suppose I have a 2x2 matrix, and I want to find its eigenvalues and eigenvectors. How would I do that? Well, maybe we're not fully ready to talk about the eigenvectors, but we can certainly talk about the eigenvalues. You will never again write the characteristic equation for a 2x2 matrix and find the square roots of some, quadratic equation. That is not how us sophisticated people diagonalize 2x2 matrices. We just look at it because we can always express it in terms of a superposition of the identity and the Paulis. Okay? So the first question I have for you, if I have a matrix, I can always express it in this form, either by I or by looking at the components in terms of the Paulis. I can figure out what these components are. So now I've done that. I have this parameterization. And now I ask, what are the eigenvalues of this matrix? I'm listening. Yeah, so let us note that I can write, let's say that the vector A has some magnitude and some direction. Okay? It's a vector. This is just the direction of that vector. Right? I could always find that. So now I write A as A naught over 2 plus on the 1, 2, 3. It's there. Sorry for that notational problem. Right? You with me? Okay. The eigenvalues of this operator are what? Well, this is the Pauli matrix along some direction. If this was the z direction, what would be the eigenvalues of this matrix? Plus or minus 1. If this was the y direction, what would be the eigenvalues of this matrix? Plus or minus 1. If this is any old direction, what are the eigenvalues of this matrix? Plus or minus 1. Therefore, the eigenvalues of this matrix are A0 plus or minus the magnitude of A over 2. That's it. That's how you find the eigenvalues of the 2-digit matrix. What are the eigenvectors? Well, they're the eigenvectors of this, because anything that's an eigenvector of that is also the eigenvector of the identity. So what are the eigenvectors of this operator? Well, they are spin up and spin down along that direction. So the eigenvalue with up is spin up along that direction, and the other one is spin down along that direction. And that, my friends, you should ingrain in your mind. That's how you think about a 2-digit matrix. All right. Now, when thinking about angular momentum, it's very important to think about angular momentum as the generator of rotations. So let's review that. We'll get somewhere through that, but not the whole thing, it seems.
Can I ask you a question?
Yes, I'm listening.
Is it assumed that capital A is Hermitian?
Oh, that's a good point. Yes, if I'm going to talk about the eigenvalues of vectors, absolutely. This formula is general,
Right.
whether or not this is a Hermitian matrix or not. But my procedure that this is a real vector with a real direction, assume this was Hermitian. Otherwise, I couldn't diagonalize it for unitary. I could do that. But you're right. Thank you for clarifying that point. This formula is general, but this procedure is only true if this is Hermitian. Yes. All right. So, spin angular momentum and rotations. All right. So, if I have a vector v, I can think about some axis of rotation and rotating this by some angle theta. Okay. That's capital theta, not the circle H branch. It's another story. Anyway, so that gives me a rotation which, if I were to look at that, I could say there's some rotation on the vector v. We have some components, that's the sum of some rotation matrix on the vector. Okay. Now in quantum mechanics, such an operation is what's the word I'm looking, the verb I'm looking for? Is implemented by a unitary transformation. And that unitary transformation is rotate by that angle theta generated by the angular momentum along that direction, along that axis. By h bar. So if it's a spin angular momentum, it would be that. This is a rotation operator on Hilbert space. Now this is going to be confusing sometimes. We have two kinds of what we call rotations. We have rotations in Hilbert space and rotations in physical space, R3. And there's intimate relations between them, and there's confusing relations between them. But they're two spaces and they're connected. Okay? Right. So, this operator, of course, is written in terms of localities. Okay? And there's this over 2, importantly, because of the relationship between spin angular momentum and localities. And it drives me nuts to no end when the computer scientists who work in our field talk about pi/8 rotations when they're really pi/4 rotations, because they got a stupid pi/8 in here and they don't know that this is a rotation by pi/4, not pi/8. Anyway, rant of the day. All right, so what was I going to say? Yeah, right. So importantly, as I said, there's a relationship between these guys. So let me call this operator as the operator D around some axis by some angle. So, for example, suppose I look at a rotation around the z-axis by an angle theta. What that would do, it would take the x direction into something which is in the xy plane, cosine theta x plus sine theta y, right? That's a rotation around the z-axis by an angle theta. Now, we implement that by a unitary transformation. So if I rotate around the z-axis by theta of sigma x through this unitary transformation, and it's a passive transformation on the coordinates, that's why it's written this way, that would be sigma x cosine theta plus sigma y sine theta. It rotates the components just like it rotated these components. So notice, on the left-hand side, I have a unitary transformation on the operator. And the right-hand side, I have something that looks like a rotation matrix in x and y components that combines those components. This connects what happens in Hilbert space to what happens as a physical rotation of x and y components. Right. Okay, very good. So, let's see, let me just see what I'm doing here. Right. So let's draw a three-dimensional space here, x, y, z. And let's say I have some arbitrary direction in space. It has some polar angle in spherical coordinates, theta and phi. So E sub n is just a unit some direction in space denoted by those directions, okay? Now, there exists a rotation in R3 that takes the z direction, say, to En. So, if there is that, whatever rotation that is, I could, for example, write it, there's some axis and some angle which takes this direction into that direction. Thus, this guy takes this, by what we just said, into the Pauli matrix along that direction, which I'll call sigma sub n. In the same way that this rotation took the x direction to that direction, it took the Pauli matrix along that direction to that direction. This rotation takes the z-axis to this direction, therefore it takes the z-axis to that direction. So this is the unitary transformation. It better have a dagger or else it doesn't make sense in exactly the same way. Okay. So the claim thus is that the eigenvectors of sigma z are thus, I take the same rotation matrix, which takes the z direction to that direction, and apply it to the eigenvectors that is to say, the rotation matrix that takes one direction in physical space to another direction in physical space takes the spin along that direction, initial direction, the spin in that final direction. Okay? So this is how a rotation matrix in physical space acts on the vectors in Hilbert space. So for example, I can write this guy in the following way. First, rotate around the y-axis by the polar angle theta, and then around the z-axis by phi. That will take this vector along z, rotate it by theta, and then swing it around the z-axis by phi and move it to there. Right? You see that geometry? Therefore, if I take this, if I want to know what is the spin along that direction up, I can obtain that by first rotating spin along z by y and then around the z-axis by phi. So what we need to do next, and we'll save that for next time, is what are these rotation matrices? How do I write them so that I can do this operation on this? So that I can learn the very important fact is, how do I write the spin along any direction n as some superposition of spin up along z and spin down along z? Because any vector in Hilbert space in 2D is a superposition of spin up along z and spin down along z. If it's spin up along some funky chicken direction, then I need to know what those probability amplitudes are. And I can get those probability amplitudes in this way. And we'll do that next time. This is extremely important foundation that we're going to use all the time. We need to know everything there is to know about two-dimensional systems. And that means knowing everything there is to know about spin 1/2. So I encourage you to review that in your previous courses if you're not, it's not